Good morning, everyone. Thank you for joining us. I'll just give it a couple more minutes just to allow people to log on before we start. Okay, so hello and welcome to today's ECA Learning Zone webinar on RCD considerations for renewable technology with Hager. My name is Elena Carrasco and I am ECA's Communications Manager. Today I am joined by Paul Chaffers and Paul Collins, who are both technical training managers at Hager. Just want to cover a couple of housekeeping points with you before we enter the webinar session properly. All views expressed in this webinar are solely from the perspective of Hager. The webinar has been organised by ECA as part of its commercial associate scheme. This webinar is being recorded and will be made available soon after this session via the ECA website. At the end of the session, there will be a QR code for you to scan where you can claim your professional development certificate as well. And finally, there is a Q&A tab at the top of your screens. Please post your questions in there throughout the webinar for the presenters to pick up at the end of their presentation. You can also vote on other people's questions. The more votes a question gets, the further up the wall it will go. This will highlight the more pressing questions that you want to be answered. So without further ado, I'll hand over to Paul Chaffers.
Thanks very much. Good morning, everybody. Yeah, it's going to be a great little webinar, this one. We're going to be talking about lots of interesting things. I've got the content of the webinar on the screen there. Over recent years, we've had lots and lots of different wiring regulations that have come in that have called for different types of RCD. So I think we're going to have a run through and a reminder of what those different types are. And then we're going to look at heat pump in particular, because Hager have been on a bit of a journey this last year with Valent. We've sort of partnered with them to solve a solution, really, a nuisance tripping problem. So we're going to tell you about that and about the device that we've introduced to the market. With that, there was lots and lots of questions about how the device operated, so we're going to cover those frequently asked questions off. Then we're going to look at RCD coordination. When we talk about RCD coordination, it's a term that we use when we talk about different types of RCDs. We have RCD selection and we have RCD coordination, so we're going to look through that. Obviously, when we introduce some of these new devices, they may cause connection issues. So we're going to look at the issues and what the possible solutions are. And then lastly, we're going to look at, the focus is going to be on solar PV. We're going to look at bidirectional energy flow, some requirements of the protective device, and requirements considering assembly ratings of equipment when we include generators. So it's quite a packed webinar, and hopefully you'll find it useful. So to start with, we're going to look at regulation 53133, and this is the regulation that sort of goes along the lines that there are different RCDs that exist, and you as the designer or the installer have to choose the appropriate device depending on how it behaves in the presence of frequency and DC components. So I'm going to ask Paul to take you through this.
Yeah, thanks, Paul. So, yeah, good morning, everyone. So, yeah, RCD selection did become a little bit more complicated recently. Well, not so recent, actually, with the 18th edition, where we was introduced with these different types of RCDs. And as Paul said, then it would become the designer and installer's responsibility to choose the correct RCD for the type of load that they're going to be connected to. So, essentially, there's 4 types of RCDs. recognised in BSM 671, and they get kind of more complex, if you like, as we go down this line of 4. So initially we had the type AC RCD. Now, a few years ago, this would have been called the general purpose RCD. Now, the slight issue with the type AC RCD, due to its name, of course, it can detect and respond to AC sinusoidal wave only. So the symbol there shows you what it does. It actually has to have a sinusoidal current wave as a fault wave going to Earth to actually do the detecting and therefore the disconnection. Now, that's fine as long as we have only resistive loads. And so you have a purely AC sinusoidal wave that is the Earth fault current wave. But that's unlikely in today's modern installations where we have a lot of electronics. So although they can still be used in BSM 671 in the current edition, okay, you've got to be very careful, and it's only resistive loads only. So that's why we put a cross through this one. So as soon as you have any kind of electronic controls, it's a chance of it not being a pure AC sinusoidal wave. So really, the type A is now the general purpose RCD we have today. And manufacturers like us, of course, if you have a standard consumer unit with standard RCCBs or RCBOs, this will generally be the RCD type that is inside that equipment. Now, what this can do, of course, it can do the sinusoidal detection as well. So as we go down this line, what you'll see is actually the symbol picture building with the other things it can do. So it can do the sinusoidal thing, so it can do everything that a type AC can do, but it can also detect and respond to pulsating DC components, which you might get from some kind of electronic equipment if there was a fault to Earth after some of the electronics. So it is possible. Now, also with this device, it has some kind of resilience, if you like, to flat DCs, which we might get from batteries or cars and things like that. So this is actually resilient to any kind of DC, flat DC of 6 milliamps. So that's another thing that the type A can do. Moving on from that, we have a further device, which, as you see, is another symbol appeared, which is kind of denoting higher frequency detection. So when we go from the change from the A to the F, we actually get a standard change as well. The AC and the A are 61008 or 61009, and the F and the one that's going to follow it is a different standard. It's a 62423 number standard. So what this does, everything that the two above can do, but this can also detect and respond to some kind of different frequencies, some higher frequencies, which we might get from variable speed or inverter equipment and things like that, that might produce a higher frequency than the standard 50 hertz. Now, this one has a slightly better resilience to a flat DC, and it can detect and respond and not get any kind of blinding issues with any DC component up to 10 milliamps. So a little bit better than the type A. Don't see many type Fs, to be honest with you, though, in the marketplace, because we normally jump, if we don't have a type A, we tend to jump to a type B, which is the best RCD out of the 4 recognised in BSM 671. Now, what this can do, everything that the above 3 can do, of course, as before, but this actually has very good resilience to flat DC. So, you see the flat DC symbol there appear. So the A and the F, why they have a resilience to this 6 milliamps or 10 milliamps DC, if it goes above that, unfortunately, these two products can actually get locked or blinded is the term that's used. Basically, they don't work. They can't work. The core's saturated. They're not able to do their job. The type B cannot be blinded, okay, because if it sees too much DC, it actually does a disconnect. You get a disconnect signal. So instead of being blinded, it disconnects. So they're the 4 RCDs that we have recognised by BS 7671. And as Paul said, it's our job as installers and designers to select the correct one. We are given guidance, of course, in 7671, but to select the correct one from the type of load we're going to be connecting it to. So hand back to you, Paul, for the next bit. Did you mute yourself, Paul? Sorry.
Thanks, thanks, Paul. Yes, I did. Happens every time. Yes, we're going to look at this slide now because obviously there's a lot of government targets for net zero, and they want to install 600,000 heat pumps annually by 2028, and you can see the growth there. Heat pump sales grew by 63% between 2023 and 2024. So it's a great opportunity for businesses to get involved in the installation of these devices. And it kind of, where it led to with our journey was that Vaillant got in touch because Hager, we actually make our own devices, and they got in touch to try and understand what the problem was. They were experienced lots of calls to their helplines and lots of nuisance tripping issues. And kind of the problem with heat pumps is usually the heating system is designed by the heating engineer, and there's quite a process they have to go through with looking at what the heat losses of the building, sizing the emitters correctly, sizing the heat pump correctly, etc., etc. But all usually they tell the electrical contractors they need a supply for a heat pump. They may say how many kilowatts the heat pump is, but that's not the electrical load, that's the heating load. And things can go wrong. So we kind of got into that conversation with Vaillant, and it took us on a bit of a journey, which we're going to share with you now. First of all, I asked Paul, what does the reg say about it?
Yeah, so we've had lots of discussions between us and obviously several other people. And ultimately, as a lot of you guys will obviously know, of course, does BS 7671 actually have any special requirements for heat pumps? Well, no, it doesn't. Okay, so there is no special location for a heat pump. There's no Part 7 section. There's no mention of the word heat pump in 7671. If you did a search, I don't think you'd even find the word heat pump. So essentially it's just a piece of equipment. So, why was we talking about the issue with RCDs and heat pumps, which we've been talking about? So there is a couple of regulations actually that kind of leads us down to that channel. We have 13411, of course, requiring workmanship and proper materials to be used, but more particularly, the installation electrical equipment shall take account of manufacturer's instructions. And this is where we kind of sent our researchers down. So looking at, so what do the manufacturers say about, the supplies to a heat pump, and why did they say it, Paul? We had to go to this road, didn't we?
We did. So we sat with a number of technical managers from different heat pump manufacturers, but Vaillant were very clear with their requirements, and this is a snippet of their instructions from their heat pump range. They're very clear that the RCD type should be type B, which Paul's already explained is the best device on the market. But they've got this statement at the bottom that all Vaillant heat pumps must be installed with a type B RCD rated to 20 kilohertz or greater, with a minimum trigger point of 150 milliamps above 1 kilohertz. So straight away it gave us a lot of concern because we're talking about very high frequencies. I'm also talking about adjusting the trigger point of the RCD when it goes above 1 kilohertz. We're all very familiar with using a 30 milliamp device to provide additional protection, and now we're looking at a device with a residual current rating of 5 times that. So quite concerning for us to start with until we understood it. So with that in mind, we started looking at what our standard devices could do, and Paul's already given you the standards for these, but the standard 62423 for the F and the B only tests and certifies the products up to 1 kilohertz. So straight away we could see that standard devices off the shelf wouldn't meet the requirements that Vaillant were looking for. And it's not just Vaillant, there was other manufacturers out there. At certain points during the switching of the inverter, it causes high frequency currents, which can cause nuisance tripping of these standard devices. So what we did at Hager is we had a chat with our development team, our engineers, and designed a device that was capable of meeting the spec that Vaillant were looking for. And we call it the type BHP. You can see an image of there. It's got it carries the standard type B symbols, but it's got a picture of a heat pump on there just to make it nice and clear in the marketplace for plumbers and heating engineers, etc., exactly what this device is for. So along the journey as well, we had a lot of conversations with some different technical managers of different organizations to get their views, and quite a few are sort of saying, well, you know, is it possible? So Paul, you know, was it possible that we could omit this RCD from the design?
Yeah, we thought this first of all, because we know we're only complying with BS 7671, of course, but we already looked at variant instructions. So, you know, some wiring methods, of course, don't require additional protection by RCD. So could we do this as well, so we don't have to actually follow this requirement from Valiant in particular? And actually, we ended up with the answer that no, you can't really, because we have to take account of the manufacturer's instructions. So, you know, again, we had to talk to the manufacturers of heat pumps. Well, why are they saying this for an RCD? So that led us into, you know, studying lots of different standards, you know, and we spent hours and hours and hours spent studying lots of different standards, this being one of them. And this particular one, household and similar electrical appliances for safety standard, Paul, this was one we had to look at a lot of times and spend a lot of times reading this one, didn't we?
It is, Paul, and I think you're right. You know, the majority of businesses out there don't usually go and you know, start looking for different appliance standards. We have the standard, you know, we've got the electrical regs, and they're probably maybe fire, emergency lighting, some of these other British standards, but this is not one that everybody has in their, you know, in their library. And when we got our hands on it, we could quite clearly see why the manufacturers were recommending an RCD, because this is a product standard for electrical heat pumps, and it's a safety standard. Okay, so within that, this is the text, what it says. It says the installation instructions for the appliance shall state that an RCD not exceeding 30 milliamps is advisable, and this is why the heat pump manufacturers are including it in their data sheets, that a 30 milliamp device should be used. Okay, so it comes from this product standard, and that made things a little bit clearer, didn't it? When we had those conversations, we could understand that it's not driven by the electrician to design it using BS 7671. It's driven by the manufacturers of the heat pump. And of course, BS 7671 tells us to take account of those instructions. We also had some questions about whether it was in scope, because the standard does talk about access to the public and different things. We had a look at the scope, and the scope is very clear. It is for household environments, including dwellings and associated buildings and the garden, etc. So very much the type of heat pumps that we were working with Valiant and the house builders that we work with, finding that solution for them was vital. So we now knew that we needed the supplier device, and we knew it needed to deal with frequency. Paul, we looked at the B+ range, didn't we?
Yeah, our German colleagues kind of highlighted this to us, and we knew of its existence, of course, but they highlighted to it in our discussions, and they said, you know, once we knew why we needed an RCD and what were the particular characteristics of that RCD, you know, it was easy for our colleagues in Germany. They just said, "Oh, just use the B+ RCD. It's you know, it can tick all those boxes." Now, if we was in Germany, that's correct. It could have ticked all those boxes. But the problem with the B+ RCD, it is a specific product for the German market. So it's a German VDE standard, and it won't be recognized, and is not recognized by BS 7671. It doesn't even have an international or harmonized, i.e. BSEN standard, that we kind of could tag onto BS 7671, if you like. So it makes it very difficult for us in the UK to use a B+ RCD. It could be used, of course. You know, we can use anything if we choose to. But the person deciding to use a B+ RCD, because it's not recognised in BS 7671, it's outside of BS 7671, and that kind of leads us on to using a departure. Now, someone, you know, using a departure, it's not as easy as it sounds. You know, that guy making the design decision to take that departure and use that departure has got to do some research and get some information. Is this the right device? Why is this the right device? is it at least as good as something that could be, you know, a product that is recognised by BSM 671? And there was a lot of ownership and responsibility on the person doing it. So, you know, once we really went down this avenue of looking at, is this possible, this B+, you know, we decided it was too problematic really for people in the UK to go through that departure process and use a B+ RCD purely because it's German standard, okay, and not an international harmonized RBSN. So we ruled this out. So that wasn't useful for us. We couldn't go down this road. So we needed a specific UK usable RCD. So we had to come up with another solution.
Okay, thanks, Paul. So yeah, obviously what we wanted to do is we wanted to keep it a type B, so it's certified to the standard that is recognised in BS 7671, but we wanted to engineer it with these extra, this extra sort of higher frequency range that Valent were asking us for. So we had to sort of get our head round it. If we produced a device that had a tripping threshold above 150 milliamps at 20 kilohertz, would it be safe? And you know, obviously, of course, Hager are not going to place a product on the market that's not safe, but we had to be satisfied with it, and we sort of started to delve into some different standards, didn't we, Paul?
Certainly did. So again, you did a lot more work than I did on this, Paul. So there's two standards which were important to understand this concept. They're both 60479 parts 1 and 2, and they're both considered effects of current on human beings and livestock. Now, part 1 is where we generally concern ourselves, because part 1 is generally the 50 hertz requirement. This is the part that tells us, you know, you need 30 milliamps, etc., for additional protection for 50 hertz. Okay, but you know, we're talking 20 kilohertz. So after I think Paul spent hours and hours reading part 1, okay, we suddenly realized, didn't you, that you was reading the wrong one. So it's back to square one and get your head in part 2.
I did, Paul. Yeah, I mean, it's a very interesting read, but yeah, it was part 2 that deals with the special aspects. So everything over 1,000 hertz is into here, and it's a standard that I'd never even, you know, considered reading before. And it's funny, as we've gone around the country presenting this webinar this year, we've not really come across anybody yet that has understood these effects of frequency on the bodies. So I'm going to try and explain that now. And when you look in the standards, there is a term, a frequency factor. So the definition for the frequency factor is the ratio of threshold current for the relevant physical effects at frequency compared to the threshold current at 50, 60 hertz. And this is figure 6, which deals with the variation of threshold of the ventricular fibrillation for the body. And as you can see, that as the frequency goes up, the body could take more current. Okay, so let's have a little look at the 20 kilohertz. That gives us a frequency factor of 300. So what this standard is telling us is that at 20 kilohertz, the body can take 300 times the current that it could at 50, 60 hertz. Okay, that's what the frequency definition is telling us with this table. So quite interesting. I thought I'll use a 30 milliamp device that we're all familiar with, and that tells us now that for the same effects as receiving 30 milliamps at 50 hertz, we could now receive 9 amps into the body at 20 kilohertz. Very sort of big numbers in terms of, you know, electrical safety when we're used to dealing in milliamps. But this is what started to build my understanding of what we needed to achieve. So next up, we looked at the you know, the ventricular fibrillation line and how the device would be mapped against it. Okay, so we looked at the standard type B, and what it does is it carries along, you could see the indicative characteristics in the blue line there, and then we've got the ventricular fibrillation in the red line. It carries along until it goes over about 100 hertz, and on the standard type B, it starts to climb. Okay, so it starts to climb. This is the current rating over here, and you can see that it's designed to do that in accordance with its product standard, and that's how it deals with the frequency. So the symbol that the F&B gets this is exactly how it deals with it. When we start to get to higher levels of frequency, the tripping trigger point is able to raise in line with this red line. So basically it's providing equivalent protection when it gets to frequency. Once we understood that, all we had to do then is ask our engineers to continue that line until they got past 20,000. Okay, this is what Valent were asking for, to get above this 150 milliamps level when we get over 20,000. Now, we could have carried on the device up here. We've already explained that you know, we would be happy to see 9 amps, but we didn't want to push it that far, and the device sort of cuts out when it gets just over, if there is a fault, it cut out just over an amp. So I hope that makes sense. Usually when we've got our live audience in front of us, I look for some nodding heads that they've understood what we're trying to say there. Essentially, all we've done is extend the characteristics and provided equivalent protection as to what you would get back here. So what we're going to do now is we're going to move on to coordination. Paul, do you want to take this bit?
Yeah, so thanks, Paul. So hopefully that's been a good explanation and understandable for everyone. I mean, it was kind of even for us a few months ago, it was well, we didn't know that, so you know, why would we expect anyone else to know that? So, but now we do. So okay, but now we know the characteristics of a certain RCD that might be required to feed this heat pump. Okay, RCD coordination may be important. I'm not talking about selectivity here. I'm talking about the coordination of different types of RCD. So if for any particular reason, and there could be a number, of course, we needed RCDs in series, okay, generally the one upstream must be better in that line of 4 or now 5 than the one downstream, or as good as, of course, not necessarily better, because obviously if the RCD has specific characteristics, the one nearest the heat pump, any faults in the heat pump, okay, will need to be seen by, could be seen by both RCDs, okay, and we don't want one upstream being blinded or affected by the operation of that particular fault current. So they have to be at least as good as, and there's a drawing from Beamer that kind of explains this a little bit better, where we have upstream and downstream RCDs. So you can see at the top there, we've got all type A RCDs and a type A selective type RCDs. That's okay, because it's as good as, it doesn't have to be better. Like I said, it's at least as good as. So the type A can feed a type A. But the type A selective, of course, may not be suitable to provide a supply to the type B HP RCD for the heat pump. So we may have to think about wiring systems, of course, okay, for the additional protection of that cable. Okay, there is some data from manufacturers like us, of course, that could say whether that type A selective may be suitable, but generally, unless you're told differently by a particular manufacturer, you can't feed what I'm going to call a worse RCD upstream from a better RCD. i.e. you should not feed a type A to an F, a type A to a B, etc. So that's the case. What we mean by RCD coordination. It's about RCDs in series. Now, this brings us on to, okay, so if you're kind of adding a heat pump to an existing installation, what are you presented with there already? Some consumer units may not be suitable to connect the heat pump and the heat pump RCD to it. For example, the one on the left there, going back a few years, of course, but it wasn't uncommon to have an RCD or RCCB, I should give its proper name, as your main switch to the installation. So wouldn't do that now, of course, but you know, it was common in, you know, a few years ago. So there are spaces there. So if there are spare ways to the left of that last MCB, could we put something there that then feeds the heat pump? Well, from what I've said just a little while ago, hopefully you can see we've got an RCCB upstream of the heat pump one, which might be affected from the characteristics of the load or any fault current actually from the heat pump. So we don't want to impair the characteristics of that RCD or RCCB, because that's providing electrical shock protection or additional protection to all the other circuits in the building. So we can't do that at that type of installation. Typically, installations from the right there a few years ago when we had split load installations where we had dual RCDs in the board. Now, every single circuit is either fed from the RCD on the right or the RCCB on the left. Okay, although there's spare ways in that board, same reason as the left-hand side. If we used one of those spare ways to feed the heat pump and then maybe the RCD in a little enclosure on its own from that to that heat pump, any kind of load current or fault current will be going through another RCCB, and those are likely to be type ACs or A's more recently. So we can't really use those two installations to feed a heat pump installation. Now, more modern boards, however, okay, still split load, the one on the left. Now, this more recently had called high integrity split load consuming unit. This kind of had the name. And with a high integrity split load consuming unit, as Paul's pointing out there, you do have a couple of circuits or a couple of ways where you can feed something else that's not going to be shared with one of the other two RCDs in the assembly. So, you know, you could put then an MCB feed in a little enclosure with the heat pump RCD in it. Of course, if you had a lot of space in that kind of gap there, you could fit an MCB and the RCD or the RCCB in that space there. So, you know, it depends how much space you've got, whether it could have gone in the same box, same assembly or not. More recently, however, I mean, I bet most of you guys, if not all of you guys, would now use RCBOs rather than split load arrangements. So with an RCBO installation, of course, you can do whichever you like. So we've got the last circuit there. You can put an MCB to feed another little assembly with for the heat pump RCD in it. Or again, if you had enough space, you could fit the RCD, the heat pump RCD in there as well. So more modern assemblies, we can get away with this. So, but if it was a more older one like before, you know, we might have to be talking like service connector blocks and things like that to actually connect the heat pump to the electrical installation, because we don't want to affect, you know, the RCDs that's there. So this could be a general assembly arrangement, and the consuming it therefore, the heat pump consuming it is a product that we've made specifically for, well, Valiant designed this for us, Paul, didn't they? So we're actually selling this to Valiant through them and their merchants.
Yeah, they sell it. It's a bespoke board with the ratings of the devices for their actual equipment. So they wanted like an RCBO for a backup heater and another device for controls, and then of course there's overcurrent protection for the RCCB that's in there. Also, they included an SPD in their box. But we sell all these loose components if someone wanted to purchase them through their regular electrical wholesaler. And there's different solutions. We do a lot of house builder boards here at Telford, don't we, Paul? And house builders typically still use the dual RCD boards. And reason being really is that they, you know, MCBs are, you know, cheaper than RCBOs, but they're starting to realise the limitations with split load boards, especially when including extra devices. So these are some of the conversations we've had, and, you know, it's possible that they could, as Paul said, on the high integrity side of the board, include the heat pump device here sitting on the DIM rail. But also, you know, if there's more circuits needed, then an RCBO board does free up that extra space, because we can now remove these two RCCBs here, plus all the link wiring and everything, which creates a cleaner, neater board, and to sit the device on the end of the rail. So that's sort of some of the concepts we looked at. Now, if you're interested in any more information about the device, on our landing page on the website, you can visit and read up about it. And also there's the manufacturer's declaration there that shows that the device does meet the standard that's recognised in the wiring regs, but it's also been engineered to work at those higher frequencies. Okay, so we've gone through the heat pump stuff now. We're just going to sort of brush on to solar considerations now, because remember, this topic is about RCD considerations when we're looking at renewable energy. Now, last year, Paul, we had the introduction of Amendment 3. Do you want to sort of tell us a bit more about this?
Yeah, so again, Paul and I work through BEMA, and it was BEMA that kind of started to realise a potential issue, actually, where we started to understand that single module RCBOs were being used to feed like the solar inverter circuit. So didn't really see a problem with that initially, but what we started to understand is that, well, actually that RCBO then, that circuit is actually feeding or could pass current in both directions. So we started to understand this kind of unidirectional or bidirectional protective device requirements. And it was Beamer and Hager mainly actually who started this awareness of that there are some potential issues with this. And if we had unidirectional devices as we know them today, feeding current in the opposite direction, okay, there is a possibility of damaging some of the electronic components in that device. And damaging a component in a kind of a single module RCBO essentially means that the RCD part of that product doesn't operate anymore. It will still work as an MCB, so it will still switch on and off, of course. So how would someone know that the RCD part of that product isn't functioning anymore? Well, the only way we know it, of course, is if someone presses the test button or comes along with test instruments to do an RCD test. Now, we all know how often the test buttons get pushed. So, we thought at committee level that wasn't a satisfactory thing to do. So we actually introduced through the IET and obviously JPEL introduced Amendment 3 a little bit earlier than we wanted to introduce Amendment 3, but because it was very important, we introduced Amendment 3 before what would have been Amendment 3 next year, which is now, of course, Amendment 4. Anyway, so how do we know devices are unidirectional or bidirectional? So, okay, they are built slightly different internally, of course, okay, but we have to mark them as a manufacturer and let people know. So what's the requirement of the standard to identify a product if it's unidirectional or bidirectional? Well, according to the standard of these devices, which is 61008, 61009, if it's important for the current flow direction, it has to be marked on it. So I don't know if you can just about see on the one on the left there, the terminal at the bottom is marked L in and the terminals at the top are marked out. So again, according to the standard, it was important. So we had to mark in and out on the product. So if it's not important, of course, then it doesn't have to be marked. So if a product is not marked in or out or line or load or some other way of indicating, current flow direction, then we can assume it is bidirectional. So the product on the right there, okay, is not marked in, out, line, load, etc. So we can assume that is a bidirectional product. MCBs as such, you're very unlikely to see in and out or line and load written on those. They are bidirectional. Okay, so now we know what's a bidirectional product. Some manufacturers actually write the word bidirectional on it. Might say that's helpful, but it isn't necessary. If it's not marked, it absolutely is bidirectional. So that's the requirements of the what happened to Amendment 3, and that's how we identify some of these products. Now, as a kind of an aside for that, we actually looked at the number of poles some of these devices switched, didn't we, Paul? And we suddenly realised actually there's something else that's probably wrong in a lot of electrical installations.
We did, Paul. Yeah, and I think the problem with the Part 7s are that Part 7s are there to supplement what the general requirements of the regs are to do. Okay, so they give you additional measures. Okay, so probably in Part 7.1.2, which deals with solar, it probably doesn't tell you to disconnect all live conductors if you're using an RCD to feed an inverter, for example. Okay, that's because those requirements are already in the general requirements in the reg. So in chapter 55 deals with other equipment, and it's this regulation here that says that where the RCD is providing additional protection for a circuit connected generator set, the RCD shall disconnect all live conductors, including neutral. Okay, so this is quite interesting because if you go back, if you're looking at maybe solar PV as part of a periodic inspection, you're now looking at the device to say, is it bidirectional? And if it is providing additional protection, so like a cable in a wall or something like that, is it switching all live conductors? Now, lots of the early RCBOs didn't switch. They had a solid neutral in there, correct, Paul?
Yeah, they were. So yeah, you have to be a little bit kind of almost like, you know, BDI'd. Actually, most of these products will have some kind of drawing on the side of them, certainly in catalogs or in the little piece of paper that comes with them, and identify that, you know, and the one there we can see that would be a little drawing that was on the side of it, and we can see that one is actually switching both the line and the neutral. So there'll be some that won't be switching line and neutral. So, you know, and there is a RAG question that deals with that, where if you come across that, and gives you some guidance on how to code these products if they're not bidirectional and if they're not double pole. So the Wine Regulations Advisory Group gives you kind of good guidance about how you find helpful information about that.
Yeah, thanks, Paul. And for anybody who's not aware, that's a Q&A section on the Electrical Safety Firsts website. So if you go there and look for the professional resources, you'll be able to find those questions that are written by that advisory group. Sorry to jump in there, Paul. Just wanted to explain that. So that one thing of the bidirectional energy flow took us to look at the switch neutral, and just below that regulation is this regulation, Paul, that deals with assembly ratings. Could you explain what that means?
Yeah, this is quite an often missed regulation as well. A lot of manufacturers will say, you know, we are solar ready, we have all the consumer units you need, okay, and they give you lead you to all the bidirectional devices and things like this. But I don't see anyone yet that tells installers any helpful information for this regulation. So, and it's in Chapter 55, of course, it's the general requirements. And it's the rating of current of an assembly, i.e. a consumer unit or any kind of distribution board. So the formula is that the rated current assembly must be greater than or equal to, of course, the sum of the supplies connected to it. So in a consumer unit now, if we're talking about, you know, a secondary parallel generator, which is a solar generator, okay, there are two forms of current coming into this consumer unit. One is the upstream protected device, i.e. the main fuse for the installation, and two is the power from the current from the generator side of it. So most domestic solar systems would be kind of a 16 amp supply. So, you know, if we wanted to fully comply with the regulations, we'd have to meet that formula. And if we had 100 amp main fuse to the electrical installation, which you could have, okay, then you would need a 116 amp rated consumer unit assembly, of which generally they don't exist. If you look at a manufacturer's guidance or data sheets or information, they will give you an INA rating or current rating for the consumer unit of 100 amps. So we wanted to make sure that you people could comply with this regulation as well. You know, we can give you the bidirectional RCBOs, of course, but we didn't want people to skip this regulation or not comply with this one. So we got together with our designers, again, here in Telford, and our guys in the laboratory, and come up with a solution that you could rate a consumer assembly to 116 amps. And it has to be like this. There's some information on the website, there's a declaration, but essentially if it's arranged like the picture there, i.e. we have up to 100 amp supply from the main supply, coming through the main switch, and the secondary supply from the inverter electrically opposite from that. So the current doesn't combine and come through the main switch and possibly draw the 116 amp into the loads. So we're not overloading the main switch. Everything's electrically opposite. So there's no point in this assembly that carries more than the original 100 amp design for this assembly. But what we had to do, of course, is make sure that nothing would overheat, because we're actually adding 16 amps worth of heat into this smallish metal box. Now, it doesn't sound a lot, 16 amps, but it could be. But it actually did have quite an effect, because the actual heat generated is a function of I squared. So, you know, 16 amp squared is would of course added quite a lot of heat to this assembly. So, you know, again, in our laboratories here, we did all the tests and to make sure that all the terminals and all the products in there and the cases and everywhere else we have to put these temperature detection thermocouples, okay, still did not negate us with compliance with the standard 61439. So there's a declaration that says this. Again, you can get this on our website. If you looked at some of the products, the main switch RCBO products that we have, either on the outer carton box or on the little label that we put inside of the manufacturing date label, okay, you'll see an INA rating of 116 amps. So, you know, we can provide a solution here that kind of ticks this box as well for you. So you don't have to, you know, depart against this regulation if you're doing a small scale solar system for a house that could have a 100 amp main fuse to the house. So I think that was about the crux of that, Paul, wasn't it? We had to do a lot of work for it.
Yeah, thanks, Paul. Yeah, obviously we focused on residential, but this regulation concerns commercial installations as well. But there's a solution for that. You know, if you've got a 125 amp supply to a board and you want solar, you'll step up to a 250 board or maybe a 400 amp board. And we go up, you know, all the way up to 4,000 amps here at Hager. So there's a solution for getting a bigger INA rating, but with consumer units there wasn't. So that's why the solution has been prepared. Now, if any of you guys took part in the draft for public comment of BS 7671, you'll see that there is some suggestions of changes to this regulations, which may introduce some possible other options. And obviously, when the regulations are released and we can all allowed to talk about it, we'll be able to talk about what the solutions are moving forward. But for now, we have a solution to meet this problem. So that kind of brings us to the end of the webinar. We've left some time for some questions. Alana, if you have any.
Always takes me a while to get back online. Thank you both for your presentation. That was really great, really informative. There aren't any questions at the moment, but if anyone has anything they want to add, please do so in the next couple of minutes. Paul, if I can just ask you to move over to the next slide, please. Thank you. So here's the QR codes where you can scan your professional development certificate and you can claim 1 hour of professional development training there for yourselves. I don't think there are any questions, which shows how much of a great presentation you guys gave, very detailed.
We've either gave great detail or we've sent them all to sleep. So,
I'm sure it's not the case.
As
you're talking about CPD there, please visit the Hager website. There's a training section on there. We do have lots of free CPD on there. It's all accredited and you can download a certificate from there also. So we've got a number of topics on there. So please help yourself there and have a look. But that's brilliant. Thanks for having us on.
Thank you both. Thank you both for the presentation and thank you all for joining us. Goodbye.